I guess it's time to start the 7th session of the DISC conference. Yeah, the first talk is on gathering on a circle with limited visibility by anonymous Oblivious robots. And yeah, Giovanni, I think, is giving the talk, right?
Yeah, thank you. And hello, everybody. This is a joint work with Giuseppe Di Luna, Ryuhei Uehara, and Yukiko Yamauchi. And we consider a swarm of robots located on a circle where every robot can move just along the circle. And they are activated or they stay still and skip a turn based on the decisions of a semi-synchronous scheduler. And robots have limited visibility, so each robot can only see a part of the circle, and it's unaware of the robots that are not in that part of the circle. It computes a destination point just based on what it sees right now. It cannot remember anything from the past. And the goal of this team of robots is to eventually gather at a point in the circle. Doesn't matter in how long, and doesn't matter where. They have to gather eventually. And we argue that the circle is, so to speak, the most general closed curve, in the sense that if we have a gathering algorithm for the circle, it works on every closed curve, because closed curves have maybe some landmarks, such as points of maximum curvature or something, where robots can gather, or they can help robots gather. So if it works on the circle, it works everywhere. Now, this is an outline of the paper. We have basically two results. One is an impossibility result for visibility range of less than half a circle. This is impossible. On the other hand, if they see everything except their opposite point, then there is an algorithm for gathering. All right, the first observation is that the initial configuration must be asymmetric, right? Because if it's symmetric, then a standard argument shows that the scheduler can always keep them symmetric. So in particular, they cannot gather in a point. They can never form an asymmetric configuration if the scheduler doesn't want. So in particular, they cannot gather. Necessary condition, rotationally asymmetric initially. All right, now let's assume that the visibility range is less than a semicircle, and let's show impossibility of gathering. The technique we use is probabilistic. That is, we randomly perturb the points on the circle, the robot's locations, and we study the algorithm behavior for a specific perturbation. And what we prove is that for an algorithm to be a gathering algorithm, each robot must stay still with probability 1. And this holds for all robots collectively. And also notice that a random perturbation is asymmetric with probability 1, which means that there is at least one configuration where all robots must be still and must stay still forever, and the configuration is asymmetric. Actually, there's a great deal of such configurations because they happen with probability 1. So gathering is impossible. On the other hand, when the visibility range is full, we have this very simple algorithm, which is we look at the angle sequence induced by the robot's locations, and we look at the robot with the lexicographically smallest angle sequence, for instance, this one. And this one will be the leader. It's unique because the configuration is asymmetric. And the leader will just move to the next robot clockwise, and while the others wait. And once there is a multiplicity point, all robots join the multiplicity point. And this, of course, works because everyone agrees on the leader. But what if visibility is limited? And let's say that a robot sees everything except just its antipodal point. So this point is invisible. It can host a robot or not. The robot doesn't know. The observing robot doesn't know. What happens here is that we can sort of extend the same technique that worked for full visibility. The robot may see a leader here, but it's not really sure that this is really the leader, because there may be another robot here, and in this case, the real leader is here. So for each robot, there are two possibilities of where the leader may be, and different robots may not agree on the two possibilities. So we have a more general algorithm that works depending on where a robot sees its two possible leaders, V of R and G of R. If they both coincide with the observing robot, then this robot behaves like in the full visibility setting. Otherwise, we have this whole bunch of other rules. If it sees itself as the leader, but if it's not sure because the leader may also be somewhere else, then it just moves halfway to the next robot. It also tries to avoid becoming antipodal to some other robot. And there is also one special move in this case when the next robot has an antipodal robot. Anyway, we have a bunch of rules that eventually guarantee that a single multiplicity point will be formed. And once this happens, we just gather in the multiplicity point, and that's it. So this is our algorithm. And to summarize, we have impossibility of gathering when the visibility range is short, less than a semicircle. And our proof of impossibility also works if the total number of robots is known. And it also works for pattern formation problems where the pattern is not centrally symmetric. So the gathering problem is just a special case of this where the pattern is a point, but we also show impossibility for any pattern formation problem where the pattern is not centrally symmetric. And then we have a gathering algorithm in the case that the robots see almost everything, all the circle except their opposite point. And we have the obvious open problem of closing this gap between seeing less than a semicircle and everything except a point. So what happens in between? Can they gather or not? And also what happens if robots are fully asynchronous, or if they fail to reach their destination point. So if they compute a destination point, but they fail to reach it, or if they don't agree on the clockwise direction. That's it. Thank you for your attention.
Yeah, thanks a lot. So there's time for questions.
Hi, I was wondering if you could overcome the requirement that the setup be asymmetric if you introduce some amount of randomness to the robot's motions so that they could break symmetry.
Yes, indeed. If you have the possibility of generating random numbers, then yes, with probability 1, you break symmetry. That's right.
And there's another question by Ben.
Hi, I have the question whether can this be extended to the case where there are more than one multiplicity points initially, because you said that the algorithm tries to form one initially and then goes from there. So if there are multiple already in the initial configuration?
Yeah, that's a good question because typical assumption for the gathering problem also in other settings is that the robots initially are all in distinct locations. So that's a fairly common assumption. And if there are more than one multiplicity point, then I don't have an answer. I don't have an algorithm. It's actually another open problem.
All right, thanks.
Yeah, the big problem here is, for example, if the two multiplicity points are opposite to each other, then they don't see each other. And
right.
the real danger here is that robots think they have gathered, but actually they have not, because there are two gathering points. So that's the main problem. In our case, if a robot sees that it's alone, so because it sees just itself and nobody else, then it assumes that everyone is gathered in the opposite point. So it just moves and then they see everybody, and then it sees everybody. But if there are two multiplicity points, then we can't do that.
One question concerning asynchronicity. So I guess in your model is you assume that the robots move to the new location within a time unit. So before, yes, like there's another activation of robots, is this right?
Yeah, they move instantly or within a time unit, and they all move at the same time.
Right. So I think yes, the arbitrary asynchronous case might then cause problems, right? If movements are not anymore instantly, because then you might run into these symmetric cases, I guess.
It causes lots of problems. Yes, that's just one problem.
Yep. Okay. Yeah, that was my guess somehow. Yeah.
Yep.
thanks a lot again. And
Okay,
so we can immediately switch to the next presentation. Yeah. So yeah, this is on spiking neural networks through the lens of streaming algorithms, and Cameron is giving the presentation. So please go ahead.
All right, great, thanks. So this is joint work with Yael Hitron and Ralph Parter. Yael made these slides and she recorded a really nice video of the longer presentation. So be sure to check that out. She couldn't do the live presentation today. What we've been looking at in sort of like a recent line of work are neural algorithms, which is a form of biological distributed algorithms. These are algorithms that receive a stream of inputs. Basically, think about like I'm sitting in this room, I'm viewing my computer screen, I'm getting sensory inputs, and these inputs are basically presented as activations of some number of input neurons. The neurons in the system communicate to each other in a very simple, using very simple dynamics. So things like if one neuron spikes, it sends out 1-bit messages to its neighbors and they spike with higher probability. So some sort of simple biologically plausible dynamics. And after receiving the inputs, the network should converge to some output that represents something about the inputs. So we have these input neurons that are presented the input. We have output neurons that their spiking determines what the output is. And then we have some set of auxiliary neurons that sort of do the processing. And our goal is to basically design networks that converge to correct outputs with good probability. And also don't use a lot of like computational resources. One of the resources we think about is sort of space, which would be the number of auxiliary neurons in the network. So we'll call this number S, and often we're trying to solve a problem on an input stream while minimizing S. So that's neural algorithms. Another area of algorithms that's studied a lot in theoretical computer science, it's something that I've worked on a fair amount, are streaming algorithms. And the setup here is trying to capture the difficulty of processing large scale data because you have limited space. So the setup is I have an input stream of items, X1, X2, X3. It's a very long input stream that I can't store, and it's presented to me one item at a time. Every time I see an item, I process that item and I update my local memory state. And I'm only allowed to have S bits of memory, where I think about S as being a lot smaller than what it would take to say, for example, just store the whole stream. After I see the whole stream, I then want to output something about it. Like I want to maybe output what was the median value I saw, or what was the most frequent value I saw, or something like this. And I want to do this in trying to minimize S. Okay, so that's the streaming model of computation. And what we're looking at in this paper at a high level is we wanted to understand the connections between these two models. So I have these two different models. Both of them are trying to process a large stream of inputs using a relatively small amount of space or a relatively small network. And we're trying to understand, are the challenges in these models somehow equivalent? Can we transfer techniques from one model to the other and vice versa? And so specifically what we're asking for is, if I have a streaming algorithm that uses S bits of space, does this imply that I have a neural algorithm that uses S bits of space or something close to S? Or sorry, if I have a streaming algorithm that uses S bits of space, does this imply that I have a neural algorithm that uses S auxiliary neurons? And the reason we're asking this question is this would mean that we can take lots of techniques from streaming algorithms and use them to implement efficient neural networks with not too many auxiliary neurons. Vice versa, we're asking, if I have a neural algorithm that uses S auxiliary neurons, can I simulate this with a streaming algorithm that just uses S or order S bits of space? And this question we're really asking because it lets us get lower bounds for neural networks. So there's tons of work on lower bounds for streaming algorithms. And this will allow us to transfer them if we can sort of simulate neural algorithms with streaming algorithms. It lets us get lower bounds in our model. So those are the two questions. There's sort of two challenges in dealing with these questions. So there's a challenge in both directions. First of all, neural algorithms, you might think they're trivially you might think that you can trivially sort of implement them using streaming algorithms. Like I have a relatively small neural network, I should be able to simulate that in a small amount of space. A major issue that we have is that in these algorithms, there's two sources of randomness. So the neurons themselves generally have random behavior. They spike randomly in response to their inputs. There's also randomness in the construction of the network. So the edges of the network might have random, the synapses in the network might have random weights on them. So it's like random connectivity in the network. And we don't really pay for storing these random edge weights, but they allow us access to persistent random bits. So it means that you can't trivially simulate a neural algorithm with a small number of neurons with a streaming algorithm with a small amount of space, because it would have to remember these random edge weights. Vice versa, streaming algorithms have an advantage in that they don't pay for their algorithm description. So a streaming algorithm, just like any normal algorithm, it has its code, and separately it has its data that it stores, and you only pay for storing this data. In a neural algorithm, the space complexity includes your current state, but it also, like the whole structure of the network, encodes the algorithm. So it's not clear that you can immediately just take a small space streaming algorithm and encode it in a spiking neural network. So those are the challenges we face. Actually, I went like a little bit fast on this, but that's fine. So let me just summarize our results. So in terms of the first challenge, we don't really fully address it, but we address it like for a large class of problems. So we basically show that we can take streaming algorithms and get neural algorithms for a large number of important problems. So two problems we tackle are two of the foundational problems in streaming computation: distinct elements and median approximation. And we show direct translations, how to simulate those algorithms with a neural network that does not use too many auxiliary neurons. We also show a more general reduction, which is we can simulate any linear sketching algorithm. This is basically any algorithm that stores a linear function of the input. And this includes a very large majority of streaming algorithms. So this lets us simulate a large majority of streaming algorithms in the neural model, although it's not a totally general simulation. So that's on the upper bound side. On the lower bound side, we show two results. Well, one is more of an observation. We observe that, first of all, if you have a lower bound in the streaming model that's based on communication complexity, it directly translates to the neural model. And then we deal with this issue of having too much randomness in the edge weights by showing a general reduction from neural algorithms to streaming algorithms, that basically, even if a neural algorithm uses a lot of randomness in its edge weights, a streaming algorithm can get around this by using a pseudo-random number generator. So this gives us a general reduction and lets us, with just logarithmic loss, translate any lower bound in the streaming model to the neural model. All right, so that wraps it up, and I can take questions. Thanks.
Yeah, thanks. So I'm kind of wondering, so the more complex the streaming algorithm, does it mean that the more fine-grained also the weights have to be set in this neural network? So does it have an effect on the kind of domain of the weights that you need?
Yeah, I sort of glossed over this, but usually in streaming algorithms, people actually do think about bit complexity in their space. So usually that means they can't be doing things like storing real numbers or having very fine probabilities. So you can translate, if you have a streaming algorithm with low bit complexity, your neural algorithm, the weights will have low bit complexity. So maybe like if it has logarithmic bit complexity, the weights will have logarithmic bit complexity. And then vice versa, if I want to simulate a neural algorithm with a streaming algorithm, basically what you can show is if the neural network's not too large, you can round the weights and round the firing probabilities, even if they're real valued, without too much loss in your probabilities. So then you can simulate in small space in the streaming algorithm. So it's sort of a technical detail that I glossed over.
Yeah. So how fine-grained would the rounding have to be? Like, what would be the domain then? It's like something that is still realizable, like logarithmic, or even some arbitrarily like sufficiently small constant, epsilon?
It would be like, so at least if I'm going from, if I have a neural algorithm and I want to simulate it as a streaming algorithm, I would say I have input length n. So I have like n, I have n items coming in that I'm processing, and say I have s auxiliary neurons. Then I need to represent weights that are polynomial, like the complexity will be polynomially small in like n and s. And so what that means is I can represent them in order log n s bits.
Oh, okay.
Yeah, so pretty reasonable. I'd
not
say.
too bad, okay.
Yeah, not too bad, I'd say. But it's like, yeah. I mean, in real life, in real life, computers have fixed constant precision, right? So it's, anyways, it's a little technical, but yeah.
Can you do you count also, let's say, the input and output? Can you use them for computation also, or they are free, and on the other hand, they are, you cannot use them?
Yeah, that's a good question. So for the input nodes for the neural network, they're only allowed to have outgoing connections because they're firing for all nodes in the neural network. Whether it fires depends on its input from the other nodes in a probabilistic decision. For the input nodes, they receive external input. So their firing is determined, that is the input. Them firing is the input to the algorithm. So they can't really be used for computation. There's no ingoing edges to them. They only have outgoing edges. The output nodes, you in theory could use them for computation, but we would count that. So the output nodes are counted in, I guess like, I actually maybe presented this in an inaccurate way. The output nodes would be counted in the space complexity of the neural network. So you could use them for computation, but don't think about them as really being distinct from the auxiliary nodes in terms of the complexity.
So let's switch over to the next presentation. So this is communication efficient self-stabilizing leader election.
Thank you. So this is a joint work with Xavier Defago, Shai Kutin, Toshi Matsuzawa, and Yasu Tamura. And I presume that we are all familiar with the leader election problem, where the input is just an undirected graph, and the goal is to elect exactly one node as the leader. And in fact, in this paper, we consider a variant of the problem where we are also supposed to construct a spanning tree of the graph rooted at the elected leader. The computational model we look at is the standard synchronous message passing, where each node is identified with a computational device, and it can communicate with its graph neighbors by means of exchanging messages. We also assume that the execution progresses in synchronous rounds. And we are interested in self-stabilizing algorithms. Those are algorithms that are guaranteed to recover from any combination of transient faults. Or more formally, we assume that the initial configuration of the algorithm, including all node variables, is determined by a malicious adversary that knows the algorithm. Nevertheless, the algorithm should be designed so that it is guaranteed to converge to a valid output within finite time, and this is also known as stabilization. Now, most of the existing literature on self-stabilizing algorithms considers stabilization time as the main complexity measure. In this paper, however, we focus on the communication overhead of the self-stabilizing algorithm, in particular on the message complexity and the bit complexity. And this turns out to be a little bit tricky when it comes to self-stabilization, because a self-stabilizing algorithm must keep on sending messages indefinitely for the purpose of detecting faults, which raises the question of how do we measure the communication overhead of a self-stabilizing algorithm. And in fact, there are two approaches for dealing with this question. The first one focuses on the pre-stabilization communication overhead. And here people are interested in bounding the total number of messages or total number of bits that the algorithm sends until it stabilizes. The second approach considers the post-stabilization communication overhead. Here, the complexity measure of choice is the stabilization bandwidth that was introduced in a seminal paper by Averbuch and Verghese. This is defined as follows. We take tau to be the stabilization time of the algorithm. And then we would like to bound the number of messages or number of bits that the algorithm sends within any time interval of length tau after it has already stabilized. So we make the assumption that the nodes know n, that is the number of nodes in the graph, or a linear approximation of n. In fact, we assume that this piece of information is hard-coded into the nodes so that it cannot be modified by the adversary. We also assume that each edge is is associated with a unique identifier represented using a logarithmic number of bits. And this identifier is also hard-coded into each of the two endpoints of the edge so that it cannot be modified by the adversary. Now our main contribution is a randomized self-stabilizing algorithms that elects a leader and constructs a spanning tree rooted at that leader. And our algorithm has the following performance guarantee. So first of all, its stabilization time is O tilde of n in expectation and with high probability. The more interesting part is the communication overhead of the algorithm. So our algorithm uses constant size messages, which means that its message complexity and bit complexity are asymptotically the same. It is guaranteed to send at most O tilde of n messages before stabilization in expectation and with high probability. And after stabilization, it sends at most one message per round, which means that the stabilization bandwidth is also O tilde of n. And this, another appealing property of the algorithm is that after stabilization, it only uses edges of the constructed spanning tree. This leads me to what I regard as the main message of this paper. As far as we know, this is the first self-stabilizing algorithm for any classic distributed computing problem in general graphs that breaks the omega of m barrier, m being the number of edges, for either the pre-stabilization or the post-stabilization message complexity. And as such, it can be put in the context of the recent line of work on congest algorithms, not necessarily self-stabilizing, with a sublinear message complexity. And in fact, some of the techniques we use in our paper are borrowed from this recent literature. So that's it. If you want to hear more about the techniques or anything else, please refer to the pre-recorded longer version of this talk. Thank you for listening.
Thanks. We have time for one or two questions.
Yeah. So thanks for the talk. So you were discussing this challenge of even defining what does the communication cost of a self-stabilizing algorithm mean. And you were using one specific definition. I'm just wondering, is this definition somehow unique in the sense that it's obvious to everybody that this is the right definition, or are there some competing definitions that we should also consider here?
That's a good question. So actually, we are using two different types of communication bounds. The first one is for, as I said, pre-stabilization. I guess that for that, the natural thing to use would be just counting messages until the algorithm stabilizes. I don't think that there is any competing notion here. For post-stabilization, let me take us back to where we define it. For post-stabilization, we indeed use this notion of a stabilization bandwidth that has been out there for a long while now, and I believe that it has been considered by quite a few papers. I cannot claim that this is the only notion used for post-stabilization communication overhead. But I think that if you really want to count messages, at least as far as I know, and maybe one of my co-authors can correct me on that, this would be the most natural one.
Okay, thanks.
There is a line of research counting the number of edges that one uses after stabilization. So previously you might use all edges, and after stabilization you still need to make sure you are stabilized, like by local checking, for example. So minimizing the number of edges for local checking is also such a measure appearing in some papers. We here also use a small number of edges.
Yeah, as I said, after stabilization, we only send messages over the n-1 edges of the tree we constructed. So this is, I guess, as good as it gets, or at least in some notion.
Yeah, thanks a lot again. So yeah, let's switch over to the next presentation on type bounds for deterministic high-dimensional grid exploration.
Okay, thank you. So hi everyone, this is my talk on tight bounds for deterministic high-dimensional grid exploration. And this is joint work with Sebastian Brandt and Yara Witto. Okay, so the problem we are considering was called the ANDS problem, which stands for ANDS Nearby Treasure Search. Now, here we have some number M of agents that search a treasure that is hidden in some structure. And in our case, this is the n-dimensional grid. Now, what do we know about this structure? We know that there's an orientation. So in the two-dimensional case, think of this as each agent having a compass that points it into kind of globally consistent directions. And the agents have restricted computational power. So in our case, we consider them to have the power of a finite state automata. And initially, they all start in the same cell, but they start in different states, or think of it as each agent being governed by a different program. And the communication we allow is that agents can only communicate when they occupy the same cell. And all operations are atomic, so each agent kind of looks or senses the states of agents that are in the same cell. Then it performs some computation, which I guess is just a state transition, and then it can choose to move in one direction. So it can only move up, down, left, right, not things like diagonally and so on, and only one step at a time. And there are two variants of this model. So one is synchronous, where all agents are active at all times. And there's also the semi-synchronous variant, where an adversary can create a schedule, which agent is active at which time steps, and actually performs one of these look, compute, move cycles. Now, the objective that we are considering is to minimize the number of agents that are needed to find some treasure, or equivalently explore the entire grid. And maybe let me note one thing. So the distance to this treasure, think of this as kind of being infinite, and in particular, kind of the number of states that these agents have should not depend on this distance. Okay, so what was known? For the two-dimensional case, this was studied by Emek, Langer, Stolz, Witto, and Wattenhofer, who showed a lower bound that 2 agents do not suffice, and that 3, respectively 4 agents are sufficient in the synchronous and semi-synchronous model. And the picture was completed by Brandt, Witto, and Wattenhofer, who showed that 3 semi-synchronous agents do not suffice. Now, while the picture is fully understood in a two-dimensional case, for n-dimensional case, it was less clear. So there was recent work by Dobrev, Narayanan, Opantri, and Pankratov, who, well, the lower bounds actually just translate from the two-dimensional case, and they showed upper bounds for that 4 synchronous agents and 5 semi-synchronous agents are sufficient, and also a special case for 3 dimensions where actually 4 semi-synchronous agents are enough. And our result is that we complete this picture and show that in the deterministic case, in n dimension, the same results hold as in 2 dimensions. Now let me briefly mention how this works. So our goal is kind of to think of each point as its coordinates, and we want to find some enumeration of these coordinates such that we can go to a coordinate, go back to the origin, and then continue. Now, to kind of do this enumeration, we need some kind of notion of progress or an encoding. And kind of the key idea is that we can encode such a point as the powers of distinct primes. So we were told this is also called Gödel's encoding. And this encoding has some nice properties that we can kind of in the way that it can be manipulated by these agents. So kind of what can we do with this idea? Well, one way we can kind of store progress in some sense is to encode it as the distance between 2 agents. And what kind of information can we gain about this distance? Well, one very simple thing is actually this distance modulo some fixed number. Think of it as maybe 2. So this can be achieved by just one agent walking towards the other guy and keeping a counter modulo 2, right? Now, how can we change this value of s? We can actually multiply and divide it by, again, think of this x as being equal to 2. And maybe how this is achieved? Well, we can have these agents move at different speeds. Actually, to perform these operations, we need not only 2 agents, but a third one to help kind of in the calculations. And okay, so the main kind of challenge in using this encoding to explore the entire grid, in some sense, is that once you've reached a point, you need to go back to the origin to kind of continue, and this can be kind of equivalently formulated as kind of gaining information or changing S without losing the original value. And that is exactly the reason why this encoding I mentioned previously is helpful in this setting. Now, as a kind of brief overview of our results, well, we get these time bounds for grid exploration in n dimensions. Again, in the synchronous and semi-synchronous setting. We can also extend this to a class of unoriented grids. Now, unoriented just means that there's no kind of global direction. So the labeling kind of on edges is inconsistent. And what we show is that as long as you kind of have some guarantee that you do not always walk in a cycle, but there's some kind of way to get to infinity, this still works. And we also show that there kind of are more efficient protocols, or our techniques extend kind of by ideas from previous works to similar, to also kind of allow for some notion of polynomial time exploration. And yeah, I guess if you want to know more, please check out the full presentation. Thanks.
If you look at those tables you've shown earlier, in the big picture, randomness doesn't help in this problem?
Okay, so in the semi-synchronous 2-dimensional case, randomness does help. Okay, so maybe let me go to this picture. So using randomness, actually this red thing here, semi-synchronous one, this would be green.
Ah, right, okay, yes.
And
right.
in this case, so whether or not using randomness, you can also improve it in the n-dimensional case is an open problem.
Oh, I see. So you still don't know whether 3 and suffices for n dimensions with randomness.
Yes, exactly.
I see.
How do you measure distance? Yes, so distance is Euclidean distance, or Manhattan distance, yes, L1 distance.
So nothing more complex than that, just simple distance.
Yes, kind of in the way they move, right? They just move in a. Yes, how does the state complexity of the finite state automaton depend on the number of ants and the dimension of the grid?
Yeah, that was my question.
So I'm not sure. So the number of ants is constant. So I guess asymptotic dependency, or how it depends on the dimension, probably linearly. I don't think it's too bad.
Yeah, I guess so from your encoding, right? It looked like linear.
Yes.
But logarithmic to the distance, I guess, right? Of the treasure. I'm not completely sure, but.
I'm sorry?
No,
but logarithmic to the distance of the treasure somehow?
No, this must be, it cannot be logarithmic. I mean,
yes, the number of states should be independent of the distance to the treasure.
Ah, okay. Ah, okay.
So this is kind of the challenge. Yes.
Yeah.
Actually, I'm not quite sure about linearly, since there are some primes involved, and I guess prime density and so on. Yeah.
Mm-hmm. Okay.
Yeah, I was wondering if you can somehow trade off the number of ants and the state space of the automaton or something like that.
We haven't considered that.
Okay. Thanks.
Yeah, thanks a lot then. So let's switch to the next presentation on distributed dispatching in the parallel server model.
So, hi everyone, my name is Guy. That will give a quick overview on distributed dispatching in the parallel server model. This is a collaboration with my advisor Yora Moses and Shai Vargaptik, who is a brilliant industrial researcher working at VMware. In the parallel server model, we have a dispatcher, also known as a load balancer, that distributes arriving client requests among a set of identical servers, each with its own queue of pending jobs. The goal of the dispatcher is to distribute the jobs in a way that efficiently utilizes the servers and, in addition, provides low response times to the clients. What makes the parallel server model a challenging algorithmic task is that both job arrivals and service rates are unknown stochastic processes. This is, of course, done with the intent to capture the somewhat unpredictable nature of load balancing systems. While this standard parallel server model received a lot of attention in the literature, much less attention was given to the parallel server model with multiple dispatchers. Nevertheless, with the rapid increase in the size and volume of cloud services in data centers, architectures with multiple job dispatchers are quickly becoming the norm. The high rate of incoming requests and the demand for millisecond scale response times prevent using communication among the dispatchers for load balancing decisions. In other words, dispatchers must make immediate and independent routing decisions for every arriving request. During recent years, there were several research works addressing the multiple dispatcher case. However, all of those works still share the greedy dispatching nature of the popular join the shortest queue algorithm. Specifically, they all share the property that a dispatcher always sends its job to the best server it knows of. So what happens when we have a good server and different dispatchers that recognize it? Well, you can imagine the dispatchers as ships flocking to this good server. Now, imagine a scenario with multiple dispatchers receiving many jobs, but only a few good servers. This might lead to a herding phenomenon. A good server is targeted by many dispatchers, causing its queue to rapidly grow. This leads to a long response time, and in severe cases, the server might even drop jobs. Several existing solutions mitigate herding by relying on a lack of accurate information. But using less accurate information comes at the cost of reduced performance, since good servers might be ignored and therefore underutilized. Indeed, in current solutions, there usually exists a sweet spot in terms of available information, below which performance is poor due to insufficient information, and beyond which performance deteriorates due to herding. This led to a misconception that less accurate information leads to better performance, but this doesn't have to be the case. The key to good performance while avoiding herding is coordination among dispatchers. But dispatchers are not allowed to communicate with each other. They must make immediate and independent decisions. Nevertheless, while the dispatchers' decisions must be independent, their decision-making processes does not need to be independently optimized. We use randomness as a means to allow coordination of the decision-making processes while maintaining the independence of the decisions themselves. We formalize multiple dispatcher load balancing as a stochastic optimization problem and use the Karush-Kuhn-Tucker method to solve it. Choosing the right criterion for optimization is crucial, and you can find the exciting details in the paper. The solution, which we named tidal water filling, takes into account possible actions by other dispatchers. It has beautiful properties you can also read about. Here, we see representative simulation results for our tidal water filling policy compared to state-of-the-art algorithms. The left graph corresponds to the average performance of the system, while the graph on the right corresponds to what a client experiences. In both cases, lower is better. It is evident how tidal water filling provides the best performance in both metrics. Notice also how other solutions are better in one metric, but not as good in the other. Tidal water filling, on the other hand, is the best at both metrics. In essence, the problem of load balancing with multiple dispatchers in the parallel server model is a real-world distributed systems problem. In the paper, you can find lots of interesting and exciting details, including solutions to different dispatching constraints and partial information. We believe that many more significant contributions can be made by applying distributed systems techniques. For example, how to deal with asynchrony in the system or heterogeneity of servers and dispatchers. We discuss a few open problems in the paper. Thank you, and I hope we've piqued your curiosity about the topic.
Yeah, thanks. Any questions?
What's with the sheep?
Well, the sheep are for the herding. I feel like it's really called like that. It's called the herding in the literature of stochastic processes. They call it herding, or sometimes people call it.
Sheepdog might be better, right? Sheepdog.
Could be.
But it's interesting, quite interesting. Yeah,
Thank you.
Yeah. Any further questions?
Yeah, I was curious if your solution assumes that all dispatchers can contact all servers, and what happens if they can't?
So we assume that they can contact all servers, but if they can't, then that's a little bit of a different model, because we want to utilize all the servers And the question here is how to utilize them efficiently. So if you cannot contact the server, it's out of your question how can you utilize it?
I have a question concerning heterogeneity. So I think you do allow multiple requests to arrive at the dispatcher at the same time. And I think you also looked at this model where the dispatcher then may not have a choice. Like it cannot spread them out to multiple servers, but just to a single server, which looks to me like you might also be handling then the heterogeneous case, right? So
yeah, that's a good question. I didn't present it here, and actually it doesn't appear in the longer presentation also, because that's a different dispatching constraint that is called unsplittable, which means you have to send all this batch of jobs to the same server because they are connected somehow.
Right. I just noticed this variant in your paper, but you haven't really looked at this variant in the paper?
In the paper, we looked at it. Yeah. We analyzed it in the paper. I'm just saying not in the presentation because it's a little bit more involved technically. And the underlying principle afterwards, the solutions, they have a similar nature to the simpler one. So we chose to show the simpler one here, and people that are interested can read about the more complicated stuff in the paper.
So to a certain degree, you can already handle that.
Yeah. We handle it also much better than the other solutions that exist.
Okay, so then thanks a lot. We are perfectly in time to switch to the two brief announcements. So first, the one on reaching approximate consensus.
Thanks, Christian, and nice to see you. And my name is Louis. This is a joint work with my student. It's reaching approximate consensus when every node may crush. So the key summary, the keyword approximate consensus, and we assume asynchronous fair lossy channel, meaning that any message may be lost, but like if I send a message many times, like then the destination, if it has not crushed yet, it will definitely receive the message. And then by crush, we assume the crush recovery model. Then the exact full model is that, okay, up to F nodes, they may crush forever, and then the rest, they may crush, and then they may recover. So we have uptime and downtime. The new angle is each node has a limited size persistent storage. So if I write something into that, then later on when I recover, I can retrieve the data. And because that thing is limited in size, so simulating prior algorithm is not possible. So if you think about it, like normal way, how do we simulate reliable channel on top of fair loss channel? We kind of need to remember everything. So for example, like if I receive something, say with a tag, say that it's from run 100, but right now I'm in run 1. Then you need to remember this information until you get to run 100 to process that. But like if we only have limited size persistent storage, then we cannot write that into the storage. And then if we crush and then recover again, I will lose this information. And then under this model, actually, we can solve approximate consensus. So here's an illustration. Prior work assumed that, okay, crush with a reliable channel. So if I and J, they are both correct, then message will be delivered. And then all the good nodes, they will share common information. So approximate consensus actually is not that difficult. But for us, it's crush recovery with fair lossy channel. So that message will be lost even if that message got delivered, but the destination, it may be in the downtime, it may fail, then it will not receive. And then even if it received, but it might be out of sync. So that so what is the algorithm that can minimize the space that we need? And then in our algorithm, we only need to store 3 things. One is the state value, and then the second is a phase index, and the third one is an M-bit counter. And because we don't assume this reliable channel, and our proof is slightly more complicated, because in the old way with like reliable channel, there's a shared information, but for us, there's no such thing. Okay, and then the proof is in the paper, and we also have a follow-up work that we extend this work to Byzantine failure. We also prove the lower bound on space complexity for approximate consensus. But the more exciting direction for us is that under this model, cross recovery, and then limited persistent storage space, then what kind of tests can we solve? And that's all for my presentation. Thank you. I'm happy to take questions now.
So I guess the main difference between the asynchronous model and this crash recovery is that you only have a small persistent storage, so that you can only recover, possibly a fraction of your state.
Yes.
Right.
That's correct. Yeah, and then we need to figure out what is the important information that we need to store.
Okay.
Yeah, and then that's a limited size is what makes the simulation of reliable channel impossible.
Mm-hmm. Okay, thanks a lot. So then let's switch over to the final presentation.
Yeah, so my name is Klaus Förster, and I'm presenting work with Juho Hirvonen, Ivanon Pignole, Stefan Schmidt, and Jill Tredan on what can be perfectly rerouted locally. So we're interested in guaranteeing routing in networks, even though there are multiple link failures, and we want to do this without communication between the nodes, because by the time we have communicated, implemented new rules, we will already have lost gigabytes of data in practice. So prior work has already shown that this is impossible in general, and here we would like to go a bit more into detail. So the model is as follows. We have a connected undirected graph, and then when we forward a packet at the node, we can only match on the destination, the incident failed links, and also where we came from, because else it's easy to already have a permanent loop between two nodes. So in this context, we don't want to modify the packet, we don't want to communicate between the nodes, and to make everything fast and reliable, we want to have static routing tables and deterministic behavior. So in short, our goal is, can we install such rules ahead of time to reach the destination under any sort of edge failures, as long as the destination is still connected? And this is something that's called perfect resilience. So I would like to very briefly just show one of our main results, and namely that this perfect resilience is impossible on non-planar graphs. So if we have perfect resiliency on some graph, then also every subgraph must allow for perfect resilience, because you can create these subgraphs by just failures and then run a simulation argument. You can do this analogously for the contraction operation, where the contraction is as follows, that if you have two neighboring nodes, that you contract them to a single node, and then we have essentially a similar argument that if it works initially, it also must work under contraction. Hence, we have that if you have perfect resiliency on some graph, you also have perfect resilience on any minor of this graph, because this is exactly how minors are defined. And now we show the following, that on the complete graph with 5 nodes, the K5, and on the complete bipartite graph with 3 nodes each, K33, you cannot have perfect resilience. And hence, since these are the forbidden minors for planar graphs, we also have the result that as soon as you have a non-planar graph, you cannot have perfect resilience. So in our paper, we also have some more results. So it's not just impossible on all non-planar graphs, but already on very small planar graphs. But on the other hand, perfect resilience is possible on some planar graphs, and especially also on all outer planar graphs. And in the extended version, we also have results on more powerful routing models. For example, if you know the source, also some insights on rule space size, and we also discussed some further open questions. Thank you very much.
Yeah, thanks. So in outer planar graphs, is it somehow easy to describe how this works? Can you just in some sense go forward, or do you sometimes have to backtrack in order to?
Yes.
I don't know.
Yeah. So on outer planar graphs, this is a very simple routing algorithm from ad hoc and sensor networks, where you can just use a left-hand or right-hand rule and then just route around the outer face. And in that way, you visit all nodes and then also visit the destination.
I have a question. Does what if you move to, let's say, 2 outer planar graphs or 3 outer planar, like k outer planar graphs for a small value of k?
So how are 2 and 3 outer planar graphs defined?
Basically, if you remove all nodes on the outer plane, I mean, a k-outer planar graph is a graph in which if you remove all nodes on the outer plane, you remain with a k-1 outer planar graph.
Yes. So for one outer planar graphs, it works because then if you can remove sort of like the destination and then just route around all nodes. And as soon as you visit a node that's a neighbor of the destination, then you're done. But for two outer planar graphs, I guess the k, no. I mean, is the k, no. So that's a good question. So I would guess there's probably some threshold where it stops working, but that might be interesting to look into.
Mm-hmm. So you wrote that one of the bad graphs you considered is a planar graph with 7 nodes.
Mm-hmm.
So I guess that its outer planarity is relatively small.
Yeah.
Okay, I see. Yeah. But it is obviously not outer planar.
Yes, it's not outer planar.
Yeah. Okay, very interesting.
Okay, great. Thank you.
Yeah, so thanks a lot again to all speakers, and this ends the 7th session.